Yeah, please continue. Go on.
Okay, so this is some introductory talk about path integrals approach. Very simple example will be considered. At first, of course, as you know, if you know evolution operator, kernel or propagator, you know a solution of quantum problem. Yes, so an algorithm of determination of evolution operator or kernel is as follows. You draw all paths in the space connecting points x, t, and x prime, t prime. Next, you compute action functional for each path, among others for classical path, and you have to sum. I have not translated by all paths. Summation in Polish. The summation is by all paths. Yes, where A is a normalization factor, and this is very important that in path integrals approach, each path is assigned to each path. Some weight is assigned, weight which equals to certain number n, where the absolute value of n is equal to 1. So what we need to do, we need to add the contributions, such contributions, and each such contribution is connected to the path XA. Each path gives another value of action functional. Yes, and so corresponding contributions have different phases, and they delete each other for all paths which are far from the classical path. And that is very important and very symptomatic, and very important that if we are going far and more far from the classical path, the contributions will delete each other. And so some consideration, if you consider a close neighborhood of a classical path, the value of action functional is almost constant. So the sum of corresponding values of such contributions is large. And now, as I have said, if you if you are moving far from classical path more and more, you will have a destructive interference. So, please forgive me, because the first version of this talk was being prepared in Polish, and I have translated the majority of my talk to English. However, not all sentences have been translated, but such sentences were very small number of such fragments in Polish. The majority is in English. Okay, so the largest contribution to evolution operator is given by the paths which are close to the classical paths. So the classical paths is distinguished thanks to the fact that the contributions from the paths which are close to the classical paths, they are being added coherently. And now, for example, if we have such situation that we have a path which is far from classical path, and we can ask the question, how this path need to be far from classical path in order to the interference will be destructive. And we can give such estimation. Namely, we assume vanishing of coherence when the difference between phase of a contribution and the phase coming from the action functional for classical path is estimately equal to P. Hence, the difference between the values of action functional S and S for classical path must be equal to the Dirac constant multiplied by P. And we consider such example that we have a free particle which is starting from origin of system coordinates in the moment t equals to 0, and after, for example, 1 second, it reaches a point x0. The classical path is described by the equation, such equation. Of course, this is the usually situation in classical physics. And now we can consider another path. And the classical path is the straight line, yes, drawn by red, and another path is a curved line drawn in blue, and this line connects these points too. And this path has, of course, another equation. Okay, and let's assume that the constant alpha in the first part is equal to 1, and the x0 is equal to 1 centimeter. And now, if classical particle has mass, this is a macroscopic particle, yes, has mass, for example, 1 gram. Then, if we are going from classical path x equal to t to non-classical path x equal to square of t, we get change of action functional approximately as follows. So the phase will be changed approximately as follows. So this is very large value. In contrary, for the case of electron, which possess very, very small mass, very small mass, in comparison to the classical particle, the change of the action functional is not very large, and this equals to the 1/6 part of Dirac constant, and change of the phase is equals approximately to 1/6 of radius. So this satisfies the conditions of coherence. So if we wanted to consider electron as classical particle, and we were very obstinate, and we were saying that electron is moving along the well described path. Of course, this is in contradiction to the experiment. And now I change some notation. Now I call the evolution operator as propagator, and I denote this by key, because very often in path integral approach, people calls the propagator or evolution operator as kernel. Yes, and we assume in general that the a particle starts from the point x1 in the time t1, and the particle finish its moving in time t2 in the point x2. And of course, we have action functional as defined as usual. And of course, we assume that x dot is defined as the usual derivative of x with respect to t. And we consider a free particle. So the free particle is the simplest case in classical mechanics. Its mass is equal to m, its constants, And arbitrary path is represented in the following form. When XCL is classical path or the solution of Euler-Lagrange equation, and Y of t is a deviation of classical path. So we have also the initial conditions, yes? We impose initial conditions for the deviation as follows, and we substitute these relations, the relation between x classical and y and their derivatives, we substitute them in the Lagrangian L. And next we expand the Lagrangian around the derivative of classical path. Yes? Okay. And of course, we can write down that this integral is equal to such difference. Yes? Such difference, because we are integrating by parts. We are integrating by parts. We calculate the integral as integrating this expression by parts, and we can write down such integrals as follows. Okay, because the particle is moving without any acceleration and its velocity is constant, so we can write that the second derivative of x classical is equal to 0. Okay, so we finally obtain such situation. So we have a decomposition of the action functional as the sum of action functional for classical path and the integral corresponding to the deviation of classical path. Yes, where of course a square of the derivative of such deviation is present. So now we take into consideration this situation, so we can write our kernel in the form, yes. So I think that this is clear, because the kernel originally was as follows, yes. And of course, if we decompose the S functional as the sum, we get the following situation. The factor with this factor is excluded from the integral, and only this term is in the functional integral. Yes.
Have you missed plus? Have you missed plus between terms?
Oh, why? What plus?
In front of a to the power imaginary part over h bar s action CL plus, or no, it's multiplied. So this is
multiplied.
Okay, I see.
Mm-hmm.
So it's modulating factor. Okay, thank you.
Okay. Of course, we can compute classical action functional for free particle as follows. Yes. By the assumptions that we start from the point x1 and we reach to x2. We start in the time t1 and finish the moving in the time t2. So if we take it into consideration, if we respect this, then our expression for the kernel is equals as follows. And now we can write down this expression as follows. We have a normalization factor A, and we have to compute this normalization factor L. So we have we have an opportunity to use group property for propagators. This is very well-known group property for propagators. Yes, the propagator, such propagator we can treat as the integral of the product of of this propagator product and this propagator, and we integrate with respect to x2.
Yeah, there is a maybe interesting comment on that particular thing. So you have propagation from T1 to T3, right?
Yes.
So you have propagation from T1 to, so effectively you have propagation from T1 to T2 and from T2 to T3, right?
Mm-hmm.
But usually you have it T, so T2 is between, is bigger than T1 and smaller than T3.
Yes,
However,
yes, but this is a general relationship.
yeah, I
And
know, I know that, but
mhm,
I just want to make a
mhm.
comment on Keldysh
Uh-huh.
concepts, this particular
Yes, 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 yes.
framework. So actually, it can happen that, let's say, T2 can go to plus or minus infinity. You can go backwards and back and forth. So it doesn't have to be only chronological in between. So I'm saying that this formula can be generalized for the case of T2, for example, going to plus or minus infinity, something like that.
Mm-hmm.
Is and for having finite T1 and T3. And also, I think it can go even further. So you can play with uh, a real value time, but you can also play with complex value time. And this is the case of Keldysh contour, called Keldysh contour. So imaginary part of time is nothing else as temperature. So then you have a temperature dependent green functions, and this gives you non-equilibrium physics associated with the green functions. So that's how it is. Right. So it's just a comment. There are various notes by Maciek on that topic, and that we can in
Mm-hmm.
future can analyze a little bit deeper. Okay, go ahead, please.
So we can use such relationship. We have such situations that here appear k and k star. We have of course the Dirac function delta.
You can slightly slow down. Don't speed up. You have a bunch of slides, and let's say, uh, yeah. So could you go backwards a little bit? What it was before? What was before? Okay. Yeah. Okay. So yeah. So you have this T1 T2. Okay. And that then you define Dirac. Yeah. So in a sense, it's a propagator from T1 to T2 when they are equal, right? So you have this
Mm-hmm.
Dirac function, right?
Mm-hmm.
So
Yes.
propagation of going from T1 to T2, which is the same, which is T, and propagation going from x1 to x2 is nothing else as expressed because you have this integral. You need to put the Dirac delta.
Yes.
Yep. So it's a
Yes. Yes.
propagation to, yeah, somehow to
Yes.
stay in the same
Yes.
place.
So we use this formula, yes, and we can write the propagators k and k star with the such situation. Okay, so the Dirac function delta can be write down as follows by using these formulas,
Mhm.
and we can say that the exponential in this term, the exponent function, can be written down as follows because x2 is equal to x1 plus delta x. Yes, when delta x is tending to 0. And we denote this term as gamma, gamma of x. So we can compute, of course, the derivative of classical the action function of a classical path with respect to x0, x1, excuse me, and this is equal to such expression. And we insert this here, and we change the integration variables. We going from x to gamma, because the Jacobian contribution from Jacobian. So we change the variables in integral. If we compute this, we obtain such formula. So the square of absolute value of A is equals to this. We can write this. This term as follows. However, we can, if we look into the S classical, we can write that as the second derivative. The second derivative of S classical with respect to x1 and x. So the A of t is equals to the square root of such term. Hence, we can write down our expression for the kernel. And this is the kernel for free particle. Yes. So this is the simplest situation when we consider classical path integrals approach.
Yeah, it's a Gaussian. It's a
Gaussian, yes, this Gaussian.
Mm-hmm.
So I have such. This is end of my talk. However, this is end of my slides. However, I was wondering of the classical path integrals, and I'm wondering whether it's naive, situation. However, the classical path is as follows. Yes, for example, a straight line. Yes, from A to B, for example, or x1, x1, okay, x1, x2, and of course the other parts as follows, of course, and so far and so far and so far and so far and so far. And I have such impression because I know that you can't consider this as very naive. However, this reminds to me the situation when you have a string, vibrating string, for example, in a guitar, on another music instrument, yes? Whether this approach as a vibrating string can be applied here, and maybe some connection to, I don't know, to string theory, or maybe anyone have such idea. I don't know. However, this is my impression because each this this is very similar to the situation when you have vibration of strings.
Yeah, it is. Actually, it's a very nice. So you have this interpretation by strings, and I have this interpretation by in a sense pipe. Then you have the pipe with rubber. Then you go to the garden, and so in a sense that it's like ball that moves inside this pipe. So if we talk about string, it's interesting that okay, the simplest path is string which it has no excitation, so it has no
Yes.
lowest possible energy in a sense.
Yes.
And but you can pre-assume that for some unknown reasons the string is excited, so it is oscillating. So in a sense, it seems to me that uh, I start to be very much aligned with interpretation that nobody likes, that quantum mechanics is a classical mechanics with very special type of noise. So it's like this Nelson quantum mechanics approach,
Mm-hmm.
that that's a kind of additional noise added. So let's say this noise in your case is this energy that gives you a kind of excitation above. So imagine that you have sets, you repeat this experiment 100 times, and in most cases string is not excited, so it's straight. But if there's some, let's say, probability for there is some probability for excitation, then there is this excitation. So this shows you that there is some kind of energy, random energy flow in nature on very
Mm-hmm.
fundamental level that generates all this quantumness of things. So yes, we run right now some experiments with emulators. So we have certain circuits, classical circuits emulating quantum circuits. That's how it is, right? So
So if there would be if there will be an opportunity to use such conceptions, uh,
yeah, I mean, yeah, what I'm really thinking is that you can pre-assume there is some, the only thing which is a kind of okay, so you it's how to characterize the spectrum of excitations of classical state, or because if you have a ball moving in a pipe, in a rubber pipe, then
mhm.
from point A to B, and the walls generates a force on a particle. So this pipe does not exist. This pipe does not exist in the real world. It because you have open space and you have only potential, but somehow this walls does exist because it forces a particle to go along one trajectory. So you need to characterize the statistics. So yeah, that's a second thing. So that's how we can think on that. I think that that's quite interesting approach. And the third case, which is a kind of my favorite, is that you have a boat between points A and B on the sea, and there are some natural, you know, uh, currents in ocean. Mass flow takes place. There are currents, and the boat is drifting from a point A to B on some trajectories. So usually it's a straight trajectory, but sometimes there is a wind, and this wind gives you possibility of more complex trajectories. So what I'm saying is that path integral approach is very well embedded, very deeply present in classical physics, in classical physics, in classical statistical physics. So actually, we supposed to start learning this path integral approach not in quantum mechanics as it is by default, but by classical statistical physics, right? So let's say when you fire a, a bullet from a gun and it moves from point A to B, there is possibility of having wind. and if there is a wind, this wind generates you possible to infinite number of trajectories. Nevertheless, this wind has certain statistics of changing direction or not changing direction. So you need to so this is naturally occurring in classical statistical physics. And actually, I know people that simply deny ontology of quantum mechanics actually quite much, as this is a little bit of, or they simply say that quantum mechanics is natural extension of classical statistical physics, and that's it. And that's it. So yeah. So that's how it is. So I suggest that, yeah. So it's nice to get your slides maybe and talk to continue this talk. So if we have more questions or comments from the audience, please go ahead. Yeah. Wojciech and Eric, do you have any comments?
No.
I see. So this, Wojciech, do you have any comments?
I don't think so.
I see.
I think it was quite clear during the presentation.
Yeah. So now we want to approach this path integral approach. Yeah. So you have not yet arrived to harmonic oscillator, not yet, right, Łukasz?
No, today not, because I have not finished.
But is it possible you continue next week or something like
Yes,
that?
probably yes. For next Saturday, yes.
Yeah. Like
I must check my classes. I must check my classes because I'm not sure what about